Okay, so this is just a clarification. I won't do the whole problem, but once you see the free body diagram, I think the trick with this problem will be quickly resolved. So this is problem 180, and I had a very good question posted on Blackboard this morning, or actually it was yesterday. Looking at this pin that goes through this U-collar, isn't this in double shear? And I'm going to assume what the person was trying to do was just take the torque, divide it over the cross-sectional area, and then take it in 1/2, or something similar to that. Okay, so yeah, although this pin has two shearing areas, one on this side and one on the back side, it's not really in double shear because it's in torsion. Okay, it's not the classic double shear modality. If these were axial forces, if this were actually pulling apart, then yeah, you would be in double shear, and then the force, the shear stress on one of these shear planes would be the axial force divided by 2 over the shear cross-sectional area. Okay? All right. Well, let me just draw the free body diagram. I think it'll make it clear how a torsion is different in fact. Okay? So if we kind of just look at the top of this, here is, and I probably need to zoom out a little bit. Let's just zoom. All right. Here's that U-collar. All right, couples to here. Here's the pin going through. And then that couples to this joint, and I'm not sure which transmits or which receives, but it really doesn't matter in this problem anyway. So the two shear planes, let me get some colored markers, see if I can make this clearer. Here's one shear plane, right? And here's the other shear plane, okay? Now the force that's being applied is the torque. This way, and then there's an equal and opposite going the other way, okay? So the way I kind of drew this, I never like these curvy arrows. I tend to like putting the double arrows. So I mean this to go this way and this one to be in the opposite direction. But it really doesn't matter anyway. Okay, so let's look at one of the free body diagrams for the pin. The easiest one to look at in this case is this middle section. So I'm going to look at this middle section here. So if I draw that pin, the middle section, where we actually have kind of two cut surfaces, and you'll see it the easiest here. Well, maybe it's easier if I kind of draw it in 3D. Here's the pin in 3D. Where I've exposed, these are the cut surfaces, okay, front and back. Now what has to happen is, let's look at the front end here, okay? This is this end. This is, we can call this the x-axis if you want. There's a torque acting about this in this direction, or one direction. Actually, the book has it the other way. Okay, the book has it the other way. It really doesn't matter because I'm not going to work the whole problem out, but the book's going this way. Okay, so to resist that torque going this way, right, we need to have forces, a couple acting this way and then acting this way on the other face. So you can see this acts as a couple, all right? The other way you can do this, if you want to be a little more formal about it, you can get this by doing sum of moments, let's call this point O, about the x-axis around point O, and if you do that, that has to equal 0. Let's call this V, and this has to also be equal and opposite, but if you don't see that, you can see it the other way. And I need it tells you this distance here is 100 millimeters, okay? And so now you can see what's going on. The torque here is actually, well, this is a positive torque, okay, because it's going this way. So it's a positive torque. All right. And then this is a couple, but if you forget your couples, you can always do the moments of each force around point O. So this one gives me a negative moment. So it gives me minus V, and its moment arm is the 50 millimeters. All right. Well, well, I don't think you guys have seen this. Okay, and then this one is a also a negative moment, V. It's 50 millimeters. That has to go to 0. These can add up, so you get T minus V times 100 millimeters. All right, I mean, that's the couple force, right? That equals 0. If you don't see that the V's have to be equal, obviously they have to be equal and opposite from sum of forces. Let's call this, if this is the y direction, sum of forces in the y have to equal 0. So this is guaranteed by the fact that V equals V, right? These are in opposite directions, so they balance each other out and they keep equilibrium in the y direction. So they have to be of the same magnitude. If not, you've got an imbalance in the y direction. All right, so this allows us to get V. V is just going to be the applied torque, which is unknown because this is a design problem, over the 100 millimeters. All right. Now, the shear on each one of these surfaces is going to equal that V over the cross-sectional area, which is the pi on 4 times the diameter of that bolt squared. So this here is the diameter of the bolt. All right? So that gives you the shear. All right? Now, this is actually a design problem because it's asking you to, well, it's actually to find the maximum V that this can support with the allowable stress, okay? So just to carry it forward again, if you know this material that makes this pin will fail at 150 megapascals, and there's a factor of safety of 3, all right? That means that the allowable stress is only 50 megapascals, okay? That's the factor of safety of 3. 1/3 of the failure stress, right? That's a factor of safety of 3. That's the allowable stress. And so this, the limiting design, the Vmax is the one such that tau equals the tau allowable, right? That's what is the maximum V that can be sustained. So we can get that. So where am I? So Vmax equals the tau allowable, which is the 50, oops, I'm starting to fall off the page, the 50 megapascals, all right, times the area, which is the pi over 4. D in this case is 25 millimeters squared. All right, we'll have to do some units. That gives me Vmax. The problem, in fact, asks for the torque maximum. So we can just get that from this relationship again. So the torque maximum is 100 millimeters times the Vmax. Okay, and that's how you do that problem. And you know how to do the allowable stress stuff. That's relatively straightforward. It's the same as the other cases. But I think this is the wrinkle in the problem. Okay? Okay, if you haven't seen that before, that might not have been immediately recognizable. You don't want to, just take, well, you don't just, again, you have to think of the concept, so you don't want to just blindly get that the shear is the torque over the area. I mean, and then say it's in double shear, so we divide by 2. That's completely incorrect because, the units don't even work out, right? So you have to get force, okay? All right.
Hope that helped. Stop